Okay, picture this. You're in charge of a mining operation, but not like here on Earth. No, this is on like a massive asteroid. One of those metal-rich ones, millions of miles away.
Sounds ambitious.
Oh, it is. And here's the kicker. Your workforce, all robots.
An army of robots.
Yeah. Drilling, extracting, transporting all the valuable resources without a single human being anywhere nearby. Feels a bit like sci-fi, doesn't it?
Straight out of a movie.
But the thing is, this whole idea of robots collaborating in space, it's getting closer to reality than we might think.
Absolutely. And that's what makes this so fascinating. It's not just about sending robots out there. It's about making them work as a unit.
Right, like a well-coordinated team. Which is exactly what we're diving into today, Chapter 11. Multi-robot systems. Specifically in the exciting world of asteroid mining.
What's captivating about this field is that it's not just about sending robots to space. It's about creating a team of robots that can operate as a single, incredibly efficient unit.
Right. It's like the ultimate space age symphony or something. But
Oh.
okay, before we get too carried away with all the spaceships and lasers and stuff, let's talk about the foundation of any good team.
Coordination.
Exactly. Coordination. We humans, we kind of take teamwork for granted. But out in space, that unforgiving environment, coordination among robots can be, well, it can make or break the whole mission.
Absolutely. It's the difference between success and, well, catastrophe. Think of it like this. You have a group of dancers, right?
Yeah.
Trying to do this complex routine, but there's zero coordination.
Oh, that would be a mess.
A total disaster. They'd be bumping into each other, stepping on toes. The whole performance would just fall apart. It's the same with robots in space. No coordination. You're wasting time, energy, resources.
And potentially risking the entire mission, right?
Exactly.
So it's not just about looking all cool and synchronized. It's about, making sure the mission actually succeeds. Now, you mentioned resources. Could you maybe talk a bit more about how this coordination actually helps with resource management out there in space?
Certainly. Coordination allows for parallel task execution. And that's crucial when you have limited resources. One robot might be focused on excavating, while another one at the same time transports the material that's been extracted.
So they're not all trying to do the same thing at the same time.
Right. And this division of labor, it not only speeds things up, but it also allows the robots to specialize. They become very efficient at their specific tasks.
Like a well-oiled machine, right? Each part working in sync to achieve this common goal. But it's not just about efficiency, is it? There's also that element of resilience. What happens if one robot, has a problem out in this harsh and unpredictable environment?
That's where the real beauty of a coordinated system comes in. If one robot malfunctions, the others can adapt, take over its tasks, the mission keeps going, no interruptions. And this adaptability, it's essential, especially for those long-duration missions deep in space, where sending a repair crew is just not an option.
Makes sense. Okay, so we've established that coordination is like super important. But how do these robots actually talk to each other out there? In the vastness of space, do they like have their own special space internet or something?
That's a great question. And it's not quite as simple as setting up a Wi-Fi network on an asteroid. The chapter outlines several communication architectures, and each one has its own pros and cons.
I see.
So let's start with centralized communication.
Okay, centralized communication. So is that like having one robot, like the captain, who gives all the orders to the rest of the team?
Yeah, that's a pretty good analogy. It's like having a mission control center right here on Earth, gathering info from all the robots, making the decisions, and then sending out instructions. It's a straightforward approach, especially for those simpler missions. Make sure everyone's literally on the same page. But there is a vulnerability.
I was going to say, there's got to be a catch, right?
There is. It's the risk of a single point of failure. If that central command unit goes down, the whole system could collapse. And when you're millions of miles from Earth, sending a technician up there to fix it isn't really an option.
Yikes, that sounds like a pretty big design flaw. Are there any other ways to do it besides this all eggs in one basket approach?
There are. That's where decentralized communication comes in.
Yeah.
In this model, robots talk directly to each other. They share information, make decisions, all as a collective.
So no more relying on one single point of control.
Right.
But wouldn't that get, super complicated? Managing all those individual interactions, how do you make sure they're all working together without it turning into, total chaos?
That's the challenge. It requires more sophisticated algorithms to manage those interactions and ensure they're all still working toward those same objectives.
Like herding cats, almost.
In a way, yes. like organizing a team of highly independent individuals, each with their own strengths and, perspectives.
So it could get a bit messy. Is there a way to kind of combine the best of both worlds, like have that clear, centralized control, but also the robustness of decentralized communication?
There is. It's called hybrid communication.
Yeah.
Imagine a system where central control handles those big picture strategic decisions, while the robots themselves use decentralized communication for those real-time, moment-to-moment tasks.
So they have a boss for the overall strategy, but they can also chat amongst themselves to get the work done.
Exactly. It's about finding a balance between control and flexibility. Allows the system to adapt to, changing circumstances.
Makes sense. But how do these robots actually send those messages? Are we talking radio waves, lasers, or something even like more futuristic?
It's a fascinating mix of technologies, actually, and the choice depends on what the mission needs. One common method is radio frequency communication, RF.
RF, okay. So like a walkie-talkie system, but for robots.
Yeah, exactly. Using radio waves to transmit data.
Okay, so that's the classic approach. Reliable, relatively cheap. We know it works over long distances, but what are the drawbacks, especially in the context of space?
Well, RF signals can be prone to interference. Think about, driving through a tunnel, you lose your radio signal.
Hmm.
Now imagine trying to keep that communication going in a cluttered asteroid field, or when the asteroid itself rotates, blocking the signal. Not ideal.
No, not ideal at all. So what are the alternatives when radio waves just won't cut it?
Another option is optical communication, using lasers or LEDs. Imagine shining a laser pointer at a tiny target millions of miles away. That's the level of precision we're talking about here.
Wow, that sounds incredibly challenging.
It is. But the advantage is speed. Optical communication offers incredible speed and bandwidth, allowing for much faster data transfer compared to RF. It's like upgrading from dial-up to fiber optic.
Okay, so RF is susceptible to interference, and optical needs, like pinpoint accuracy. Are there any other ways for these space robots to communicate?
Believe it or not, acoustic communication can be used, particularly when the robots are working inside an asteroid.
Wait, using sound in space?
Yeah, it might sound strange,
Yeah.
but sound waves can travel effectively through solid materials.
Huh. That's a new one. So it seems like each communication technology has its own strengths and weaknesses. How do they decide which one to use? Do they just pick one, or is it more strategic than that?
It's rarely a pick one and you're done kind of thing.
Yeah.
It's more like you need the right tool for the right job. They might use RF for long-range communication, like between the robots and the base station back on Earth, but then switch to optical when the robots are closer together for that high-speed data transfer. And yeah, if they need to talk within the asteroid itself, well, that's when acoustic communication might be the best bet.
So it's like they've got this whole communication toolkit and they're like switching between tools depending on what they need to do.
Right.
Smart. But even with all the right tools, space itself throws in some curveballs, doesn't it? I mean, we've all experienced slow internet, dropped calls, that kind of thing. How do those robots deal with those limitations, communicating across these vast distances?
You've hit on a really important point. One of the biggest hurdles is limited bandwidth. Imagine trying to download a massive file, but you're stuck with like an old dial-up connection. It'd take forever.
Oh, tell me about it. The good old days of dial-up makes you appreciate what we have now.
Right. And in space, that data transmission, it's precious. So they have to prioritize, what information is critical, and they use these adaptive compression techniques to squeeze as much as they can into that limited bandwidth.
But even with compression, there's another challenge waiting for them. Signal loss and delays. It's like you send a message and it's like, who knows when it'll actually get there or if it will at all. How do they deal with those disruptions?
It's like trying to have a conversation, but the line keeps cutting out or your words get all garbled.
Frustrating, right? Well, robots face that all the time. Asteroid rotations, weird shapes causing interference, just the sheer vastness of space. It's a lot to contend with.
It sounds like space is a pretty hostile place for communication. So how do they overcome these obstacles? How do they make sure they can actually still work together? Relay networks are a big part of it. Think of it like setting up cell towers in space. You can have these mobile relay robots or even satellites orbiting the asteroid. And that helps extend the communication range, bypass obstacles. And to deal with that signal loss, they build in redundancy, multiple communication links. It's like having backup pathways for the data to travel.
So if one path gets blocked, it can just switch to another one.
Exactly. Always got to have a plan B,
Yeah.
or C, or D. just in case.
Makes sense when you're millions of miles from any help. Okay, so we've talked about how they communicate, how they deal with limited bandwidth, signal loss, all those quirks of trying to have a conversation in space. But the big question still remains. How do they actually coordinate their actions? It's one thing to chat, it's another thing entirely to work together seamlessly as a team.
You're absolutely right. Communication is just the first step. The real magic happens in those coordination strategies.
Hmm.
And a big part of that is task allocation, figuring out which robot is best suited for which job.
Like dividing up chores in a household. Someone washes dishes, someone takes out the trash, someone cooks dinner, except in this case, it's robots, and they're mining an asteroid.
Exactly. And one approach is static allocation. You pre-assign the tasks before the mission even launches.
Okay, so it's all planned out in advance.
Right. And that works fine for simple missions, those predictable ones. But an asteroid, that's a dynamic environment. Things change, unexpected stuff happens. They need something more flexible.
So they need a system that can adapt on the fly. What kind of strategies are we talking about here?
One fascinating method is dynamic allocation. The tasks are assigned and reassigned in real time as the situation changes.
Okay, so how does that work?
There are different ways to do it. Like they have these auction-based models.
Hold on, auctions, like robots bidding against each other. For jobs? That's kind of wild. How does it even work?
Imagine it like this. The robots are bidding on tasks. They're taking into account their capabilities, their current location, what resources they have available. And the robot that's the best fit for the job, the one that can do it most efficiently, wins the bid.
It's like a tiny little economy, but on an asteroid. But what happens if a robot keeps losing those bids? Doesn't that mean some robots will end up sidelined while others are doing all the work?
That's a good point, and that's where the design of the algorithms is crucial. You need to build, in fairness, prevent any one robot from dominating. There are mechanisms to balance the workload, make sure everyone contributes.
So it's a balance between competition and cooperation. That's fascinating. Are there any other ways they manage this whole dynamic task allocation thing?
There's also priority scheduling. Each task gets a priority level, and then the robots are assigned based on those priorities and their own availability. So the critical stuff always gets tackled first, but you still have flexibility in those assignments.
Prioritize the essentials, then fill in the gaps. Makes sense. But are there any approaches that are less about, top-down control and more about letting the robots figure things out on their own?
Absolutely. The chapter talks about swarm intelligence. Think of a colony of ants trying to find the shortest path to a food source. No one's telling each individual ant what to do. They just follow these simple local rules. But through their interactions as a group, they achieve that complex goal.
So each ant is doing its own thing, but somehow, as a group, they're incredibly efficient. How does that apply to robots, though?
Well, in a similar way, robots can engage in decentralized coordination. They each follow a set of basic rules. But through their interactions, their communication, they can achieve these complex goals without needing explicit instructions for every single step.
That's amazing. But with all these robots moving around doing their own thing, how do they avoid, bumping into each other or even crashing into the asteroid?
That's another crucial part of coordination: path planning and collision avoidance. Imagine trying to navigate a crowded room, except instead of people, you're dodging laser beams and, potential asteroid impacts.
This sounds a bit stressful.
Yeah, it's a tough challenge. But these robots, they use sophisticated algorithms and sensor data to plot their courses, avoid those obstacles, maintain safe distances.
It's like each robot has its own internal GPS and collision detection system, all working together in this crazy environment. Are there any other coordination challenges they need to overcome?
There's one more critical element: synchronization. Let's say you have a team of robots, and they're all working on a drilling operation. They need to be working together with very precise timing. Or imagine they need to all agree on a specific excavation site.
So it's not enough to be in the right place at the right time. They also have to be doing the right thing at the right time, all in sync with each other.
Precisely. Synchronization is all about making sure everyone's on the same page, operating with the same information, the same objectives, and that's where consensus algorithms come in.
Okay, so what exactly are consensus algorithms and how do they help with this whole synchronization thing?
It's like, imagine them doing a digital handshake before they take any action, just to make sure everyone's on board with the plan. These algorithms, they let the robots share information, compare their data, and basically come to a shared understanding.
Hmm.
Like where's the best spot to dig or the exact timing for a maneuver. It's all about making sure they're on the same page, even when they're spread out all over the asteroid.
It's really incredible how all these different pieces fit together, from the communication networks to those task allocation strategies and then those synchronization protocols. It really is like a symphony of robotic collaboration almost. But let's shift gears for a minute. Are there any real-world examples of this stuff in action? Have we actually seen robots working together like this in space?
Oh, absolutely. There's some really cool case studies that show how these principles are being put into practice. One is NASA's Asteroid robots up on the International Space Station. You might have seen videos of them, those little cube-shaped robots floating around.
Oh, yeah. Those are adorable. But what do those little guys have to do with asteroid mining? I mean, they're not exactly hauling rocks around, are they?
Not yet, but they're a great example of the principles we've been talking about. They use a centralized communication system, so they can be monitored and controlled from Earth, but they also use swarm algorithms for certain tasks, like moving cargo or doing inspections.
So they're like a little team of like miniature astronauts zipping around getting stuff done.
Exactly.
That's pretty awesome. What about the other case study you mentioned?
Oh, that's the Hayabusa 2 mission,
Huh?
a Japanese space probe that visited an asteroid called Ryugu. They actually deployed multiple robots on that mission, including Mascot and Minerva 2, and they used a hybrid communication system and were controlled from Earth.
Wow, so a real-life example of robots working together on an asteroid. That's amazing. What were they able to do?
They did some synchronized operations, gathered valuable data, even collected samples from the asteroid. It really showed that these communication and coordination concepts, they're not just theoretical, they're practical tools for space exploration.
It's really inspiring to see this stuff becoming a reality. It makes you wonder, what's next? What's on the horizon for this whole field of robot collaboration in space? Any exciting developments that could, like, push the boundaries even further?
The future is full of possibilities. And the chapter mentions some emerging technologies that could totally revolutionize how robots work together in space. One that stands out is quantum communication.
Quantum communication, okay. That sounds a little bit intimidating, to be honest. Can you break that down for us?
Think of it as a way to have secure and instantaneous data transfer, no matter how far apart those robots are, like telepathy, but for robots. No more worrying about delays or interference.
Wow, that would be a total game changer. What else is coming down the pipeline for these robotic explorers?
Well, there's also AI-enhanced coordination. Imagine using machine learning algorithms to make those robots even smarter, more adaptable. They could learn from their experiences, adjust their strategies on the fly, even anticipate problems before they happen.
So they'd become even better team players over time, constantly learning and improving.
Exactly. And we can also look to nature for inspiration. There's this whole field called bio-inspired communication. Scientists and engineers are studying how creatures like bees and ants communicate so effectively.
Yeah, they're incredibly efficient, those little guys.
Right. So imagine robots using similar strategies, maybe even doing their own version of the waggle dance to share info about resources or hazards.
That would be amazing to see, robots doing the waggle dance on an asteroid.
Yeah.
Okay, last question. How are we humans going to interact with these increasingly sophisticated robotic teams? Are we still going to be calling the shots from Earth, or will those control centers of the future look a lot different?
That's where the idea of holographic interfaces comes in. Picture a control center, but instead of screens, you have these 3D visualizations of the robots and their environment. It would be like stepping right into a virtual representation of that asteroid.
Wow, like something out of a movie. So, to wrap things up, we've covered a lot of ground today. We started by looking at why coordination is so vital for robots out in space, and then we delved into the different ways they communicate, how they delegate tasks, synchronize their actions, even how they avoid bumping into each other in this vast, unpredictable environment. And then we even took a peek into the future, where advancements like quantum communication and AI could completely change the game. It's clear that robotic collaboration, it's not just a technological marvel. It's a testament to human ingenuity, our desire to explore, and our ability to create systems that can thrive in some of the most challenging environments imaginable.
It has been quite a journey, hasn't it? And I think the key takeaway is this. Seamless coordination, it's not just about having the coolest, most advanced technology. It's about understanding those unique challenges of the environment and designing systems that can adapt, learn, and work together to achieve those extraordinary things.
Absolutely. And on that note, here's a final thought for you to ponder as we wrap up our deep dive. If we can master robot collaboration in the harshness of space, imagine what we could do here on Earth. Think about those complex problems we face: disaster relief, environmental monitoring, managing our growing cities. Could we apply these same principles, these same strategies to tackle those challenges? The potential is immense.
It really is. The lessons we learn from robotics in space, they have the power to transform how we approach challenges here at home. It's an incredibly exciting time to be witnessing this evolution of these intelligent systems and the boundless possibilities of collaboration, both in space and here on Earth.
Yeah.